In this video, we will examine the solutions to the questions on the first tutorial sheet. Alright, so we'll begin with question 1. So question 1 says a force vector has a magnitude of 575 newtons and points at an angle of 36 degrees below the positive x-axis. What are A, the scalar component, and B, the y scalar component of the vector? So first, we represent the situation on a simple vector diagram. All right. So we draw our x and y axes. So this is our positive x, positive y, as indicated. And the force vector has a magnitude 575 newtons and pointed an angle of 36 degrees below the positive x-axis. So we'll need the negative y component, so let's call this minus y, and of course our vector 36 degrees below the positive x-axis, so it's looking something like this, right? And this angle of course is 36 degrees, and the magnitude of a force, let's call the force F, and that value is 575 newtons. Right? So part A, they want us to find the x scalar component and B, the y scalar component. Now basically we see that this force is acting downwards of the positive x-axis, and we will resolve it into its components. So it will have an x component acting in that direction and a y component acting in this direction, right? So in terms of its components, the x component will be acting in that direction and the y component in this direction, right? And of course the angle remains at 36 degrees to the positive x-axis, right? So the x component, let's call it fx, equals, now this component is acting in the positive x direction, and typically our convention is that in that direction the vectors will be treated as being positive. So because this component run adjacent to the angle of 30 degrees, then basically this component will be in terms of the cosine of the angle. So fx is equal to 575 cos 36 degrees. Now this component, the y component, let's call it fy, equals, now this component goes in the negative y direction, and of course usually we assume that these vectors will have a negative sign, so we put a minus sign in front, and this will be minus 575 sine 36 degrees, and we work out their magnitudes. So this one is approximately 465 newtons. That's the x component, and the y component is approximately minus 338 newtons. So there we have our first question, right? Now let's look at the second question. The tutorial sheet says that three displacement vectors in the drawing have magnitudes A equals 5 meters, B equals 5 meters, and C equals 4 meters. Find the resultant magnitude and direction angle of the three vectors by means of the component method. Express the directional angle as an angle above the positive or negative x-axis. So our diagram looks something like this. Alright, so this is our plus y minus y plus x minus x. So our displacement vectors are B, which acts at 60 degrees to the positive x-axis, above the positive x-axis. We have A, so these are vectors. We have A, which acts at 20 degrees above the negative x-axis, and we have vector C, which is acting along the direction of the negative y-axis. So this is vector C, and we're told that the magnitude of A, so the magnitude of A is equal to 5 meters. The magnitude of B is equal to 5 meters as well, and the magnitude of C is equal to 4 meters. And what we're told to do is to find the resultant magnitude and direction of the three vectors by means of the component method. And of course, we want us to express the direction as an angle above the positive or negative x-axis. So firstly, we'll examine each of these vectors and we will resolve them into their respective x and y components where possible. So let's first look at vector A. So vector A. Now vector A acts at an angle of 20 degrees above the negative x-axis. Now vector A will have two components. One component acting vertically upwards, that is along the positive y-axis, and it will have another component acting horizontally to the left, that is in the direction of the negative y-axis, x-axis rather. So we'll call this component AY and this component AX, right? And of course this angle is still 20 degrees. So for vector A, its x component is given as AX equals 5, or minus 5 rather, cos 20, because generally vectors in that direction, negative x, are treated as being negative, right? So for the y component, we have AY equals 5 sine 20 degrees. So let me just put some space for the actual magnitude here. So we'll give this value soon, right? And AY equals 5 sine 20 degrees, and we work out that value. Good? Now for B will have two perpendicular components. It will have a component in the positive y direction, we call that BY, and it will have a component in the positive x direction, we call that BX. This angle, of course, is still 60 degrees, right? Now, so for vector B, its components are BX equal, so magnitude of B is 5, this is 5 cos 60, because this component is adjacent to the angle, right? So this is equal to 5 cos 60. I know that the cos of 60 degrees, that is equal to a half, so half of 0.5, that is equal to 2.5 meters, right? Now the y component, BY, would be equal to 5 sine 60. Sine 60, 0.866 or root 3 over 2. So that gives us 4.33 newtons. Sorry, meters, right? And now C, vector C. Now vector C is acting vertically along the negative y-axis, and it will therefore have no x component. For completeness, we just write Cx equals 0, right? So a vector can have no component in a perpendicular direction to which it is acting. So Cx equals 0, and of course its y component is the exact magnitude of the vector since it's acting in that direction. But of course it's in the negative y direction, and so we say that Cy equals minus 4 meters. Alright, so let's jot down the values of these missing components. So 5 cos 20, so 4.7 meters, minus 4.7 rather, and 5 sine 20, 1.7 meters. Right? Now that we've resolved each of these vectors into their respective x and y components, what we will do is then to add the components in each direction to give a single component, and then we'll use Pythagoras' theorem to find the resultant. So let's call the resultant x component, let's call this Rx. So for the x direction, so we can say Rx is equal to Ax plus Bx plus Cx. And this gives us 4.7 minus 4.7 rather, minus 4.7 plus 2.5, and that gives us minus 2.2 meters. So the sign, of course, is important because it tells us the direction or the particular axis along which the vector is acting, right? So minus 4.7 plus 2.5, that gives us minus 2.2 meters. Now for Ry, we'll do something similar. So Ry is equal to Ay plus By plus Cy. So we have 1.7 plus 4.33 plus minus 4. So let's call this 4.3 for ease of calculation to one decimal place, right? 4.3. So 1.7 plus 4.3, that is 6. 6 plus minus 4, then that is equal to plus 2.0 meters. So plus 2.0 meters. So now that we've managed to reduce these components to a single component in the x and y direction, we can then represent them on the diagram and use Pythagoras' theorem to find the resultant. So let's proceed to do this. So in the x direction, we have a vector of component minus 2.2, which of course acts in the negative x direction. So it basically acts like this, right? And in the y direction, we have plus 2. So this is minus 2.2, this is 2.0, right? If you just redraw this diagram, so the vectors run tip to tail, then it looks like this. And this represents our resultant R. So this is our x component, so this is minus 2.2, and this is our y component, 2.0, and let's call this angle theta, right? Now that we've resolved or we've reduced the diagram to perpendicular components acting tip to tail, we'll proceed to finding the magnitude of the resultant using Pythagoras' theorem and the trig ratio to find the angle theta. So by Pythagoras' theorem, we can see that R is equal to 2.0 squared plus minus 2.2 squared. So R is equal to 4 plus 4.84. So r squared rather, r squared. So r squared is equal to 8.84. This of course will be meter squared. And so r is equal to square root of 8.84, which gives us 2.97. So 2.97 meters. Right? Now we need to find the direction. So this is angle theta. We have the opposite, we have the adjacent. Now in finding the angle, we will simply disregard the sign of the x component, because we're going to, since we already established that the angle will be above the negative x-axis, so we'll just disregard the sign. So we can say that tan theta is equal to opposite over adjacent. So that is equal to 2 divided by 2.2. That is 0.91. And therefore theta is equal to tan inverse of 0.91, which is equal to 42.3 degrees. So this is 42.3 degrees above the negative axis, x-axis. So this is 42.3 degrees above the negative x-axis. Right? So therefore, our magnitude or our resultant displacement is of magnitude 2.97 meters, and it acts at an angle of 42.3 degrees above the negative x-axis. So we managed to find not only the magnitude of our resultant displacement, but the direction as well. And we've expressed that direction as requested in terms of the, well, above the negative x-axis. So we continue with the next question on our tutorial sheet. Question 3. The magnitudes of the four displacement vectors shown in the drawing are A equals 16 meters, B equals 11 meters, C equals 12 meters, and D equals 26.0 meters. Determine the magnitude and directional angle for the resultant that occurs when these vectors are added together. So we'll draw the diagram to represent the situation. Alright, so we have our plus y minus y plus x minus x. So we have vector A acting in this direction at an angle of 20 degrees above the negative x-axis. We have vector C acting in this direction at an angle of 35 degrees below the negative x-axis. We have vector B acting vertically along the positive y-axis, and we have vector D acting in this direction at an angle of 50 degrees below the positive x-axis. So we'll use the method of components to find the resultant of these vectors. So firstly, what we will do is to basically resolve these vectors into their respective components in the y and x directions respectively. Now let's start with vector A. Vector A is acting in this direction, and it will have two components. It will have a component acting in this direction in terms of the in the negative x direction, and it will have a vertical component acting in the positive y direction. And this angle is still 20 degrees. Right? So we'll call this component AY and this component AX. Vector C, we'll resolve that as well into its components. It will have an x component in this direction. Try to draw the line as horizontal as possible. And it will also have a vertical component in the negative y direction. And this angle, of course, is 35 degrees. So the x component, let's call this CX, and of course call this CY. B is acting vertically along the y-axis and therefore has no x component. D, acting in this direction, will have a component which is parallel to the negative y-axis and a component which is parallel to the positive x-axis. This angle is still 50 degrees. So we'll call this dx and we'll call this dy. Alright? Now what we'll do is to basically resolve them and put down their values, and we'll add all the x components together and the y components together. Now we must remember that components or vectors acting along the positive x direction are positive, those in the negative x are negative, and the same principle applies to the y direction. Alright? So let's go ahead and work out these components for each of these respective vectors. So let's start with A. So for vector A, so AX, so the magnitude of A is 16, and because AX runs in the negative x direction, it will carry a negative sign. So this is equal to minus 16 cos 20 degrees. And it's cos because it is adjacent to the angle, right? And we'll leave some space to put in that value. For AY, now AY acts in the positive y direction and will therefore carry a positive sign. So AY is equal to 16 sine 20 degrees, and we'll work out that value. Alright? We'll continue with B. Now vector B acts along the positive y-axis, and therefore it has no x component, or we say that its x component is equal to 0. So therefore bx is equal to 0. Right? Now the y component will be exactly equal to the actual magnitude of the vector. And so therefore by is equal to 11.0. Right? Now let's look at C. Now C, vector C, acts in this direction between the negative and x and y axes. Its component Cx is acting to the left in the negative x direction and will therefore carry a negative sign. Likewise, its y component is acting in the negative direction and will also carry a negative sign. Alright? So therefore we have Cx equals minus, the magnitude of C is 12, so this is minus 12 cos 35 degrees. And the value of Cy, again it will be negative, minus 12.5 sine 35 degrees. Lastly, we look at D. Now D has components dx which run in the positive x direction and will therefore carry a positive sign, and it has a component dy which runs in the negative direction and therefore carries a negative sign. And so dx equals, the magnitude of D is 26. This is 26.0, or just 26 cos 50 degrees. And lastly, dy equals minus 26 sine 50 degrees. So we'll now work out the magnitude of these components, right? So 16 cos 20 so this is minus 15.0. No need to work that out. 12 cos 35 or minus 12 cos 35. This is minus 9.8. And dx 26 cos 50, 16.7. We come over to the y components. So ay 16 sine 20. This is 5.5 to 1 decimal place. No need to work that out there. 12.5 sine 30 or minus 12.5 sine 35 rather. Oh, not 12.5 but 12. So minus 12 sine 35. So minus 12 sine 35. So this is vector Cx. 12 sine minus 12 sine 35. This is minus 6.9. So when dealing with our vector components, you must be careful with our signs, because if we simply omit a minus sign where there's supposed to be one, then our final answer will be incorrect, right? So you must be careful with the directions and the respective signs for these components. For dy, which acts in the negative y direction, is going to be given as 26 sine 50 or minus 26 sine 50. 26 sine 50. And that gives us minus 19.9. Right? So we'll just check to make sure that our respective components have their correct signs. So ax negative minus 15, ay positive plus 5.5, by is 11.0. It has no x component, so bx equals 0. Cx acting to the left will have a negative value, minus 9.8. Cy acting vertically downwards will also have a negative value, minus 6.9. Dx acting to the right will have a positive value, 16.7. And dy acting in the negative y direction will also have a negative value, minus 19.9. So having checked that, we now proceed to calculating the sum of these resultants in the x and y directions respectively. So for the, let's say Rx is equal to Ax plus Bx plus Cx plus Dx. And so this gives us minus 15 plus minus 9.8 plus 16.7. So this is minus 15.0 plus 0. Let's just put it minus 9.8 plus 16.7. What does that give us? So negative 15 minus 9.8 plus 16.7 equals. This gives us minus 8.1. And again, the minus sign tells us whether it's acting along a positive direction or a negative direction. So for the y component, similarly, we have Ry is equal to Ay plus By plus Cy plus Dy. And so this gives us 5.5 plus 11.0 minus 6.9 minus 19.9. So we have 16.5 minus 6.9 minus 19.9. And this gives us minus 10.3. So now that we've expressed our components in terms of a single x and a single y component, we'll then represent them using a pair of x and y axes, and then we'll add them using Pythagoras' theorem. So minus 8.1, which is the negative x direction, minus 10.3, negative y direction. So our two vectors basically look like this. right? So this is basically our Rx, that is our Ry. So this is minus 8.1 minus 10.3. We then basically redraw the diagram to show this basically running from tip to tail. So we can simply, let's do it here. Right? So this of course is a right angle. This is minus 8.1 and this is minus 10.3, and let's call this our angle theta, which is given with respect to the negative x-axis. Right? So let's work out the magnitude now by Pythagoras' theorem. So by Pythagoras' theorem, of course, our resultant, let's call it r. So by Pythagoras' theorem, we have r squared is equal to minus 8.1 squared plus minus 10.3 squared. And so r is equal to the square root of all of that, minus 8.1 squared plus minus 10.3 squared. Alright, so we work that out. R equals this gives us 13.1, and because it's a displacement now, we put the unit 13.1 meters. We're not finished though. Remember, we're dealing with vectors, and so we must also calculate the direction. So having calculated the magnitude, we must now find the direction. And so let's do the, where do we have space? So alright, so let's look at the angle here. We can say tan theta is equal to opposite over adjacent. Now basically, when finding the tangent of the angle, we simply disregard the signs, right? The signs are just there to show the orientation of the particular vectors. So we just ignore the signs when dealing with the angle, right? So tan theta equals opposite over adjacent. So we can say tan theta equals 10.3 over 8.1, which gives us about 1.25, something around there. 10.3 divided by 8.1, right, 1.27. So theta equals tan inverse of 1.27. So second function tan 1.27 equals, so 51.8. So theta equals 51.8 degrees. And this angle, of course, is below the negative x-axis. How do we know it's a negative x-axis? Because the resultant x component is minus 8.1, so it's acting in the negative x direction, and as can be seen from the diagram, this angle is acting below that. So we can therefore say our resultant displacement r equals 13.1 meters at 51.8 degrees below the negative x-axis.